Welcome back to the Data Digest and a very special video in which I want to show you over 100 basic R functions. I've been using R for more than 10 years and some of these functions I still use regularly during my data analysis. All of these functions are available to you the moment you start R or RStudio, so no extra packages are necessary to follow along. If you're very new to R, then I promise you that watching the next 80 minutes will save you many hours of frustration because I show you some of the most useful and easy R functions for data analysis, statistics and plotting. If you're already experienced with R, feel free to make use of the table of content posted below to jump to certain chapters or functions that interest you the most. I will start with some R 101 that is necessary to program in R and then show you some functions that are a bit more connected to objects like tables or data frames. You can also use R as a big calculator and for statistical tests, and at the end I will show you some basic string manipulations and how to manage your workspace, like changing the directory, loading and saving files, etc. Making this video took me over 20 hours of recording and editing, and I hope you will watch and enjoy it and learn a lot about basic R functions. Let's get started. Okay, so I just created a new script in RStudio. The environment is still empty and there are no plots yet, so we can minimize these windows and focus on the script and on the console. Let's start with the C function, which allows you to combine, for example, numbers. You have to separate them with a comma, and here I combined the first 8 prime numbers. You can execute them by clicking on this arrow to run the current line or selection of code in the console, or you press Ctrl Enter. The space between the values does not matter, so you get the same combination of numbers regardless of whether you have no space or a lot of space between the value and the next comma. And if you try to run the combine function with a value missing after the comma, you will get an error telling you that there is an argument 3 expected, but it's empty. So what does the C function actually do? You can find that out by including it in the str function. And it will tell you that with the C function and these 8 numbers, you generate a vector that contains 8 numbers. If you try to include a character string with the starting numbers of the Fibonacci sequence, it will wrap these numbers in quotes, and str reveals that you now have a vector with 9 entries, but all of them are characters. So you cannot combine different types of values within the C function. So within the console, you can use the arrows to move up and down between code that you executed before. And if you add the sum function around these first 8 prime numbers, it will add up all the individual numbers, but you cannot do that for the Fibonacci sequence because these were all characters, and you will get an error telling you that the type is invalid for the summation because it contains character values. Now, a very important function is the help function because it gives you information about what the function does. So C combines values into a vector or a list, and then you often have examples that you can run directly in the help window to see what the execution of this code will give you. So help on str tells you that it gives you the structure of an arbitrary R object. You don't have to type help. The question mark is sufficient enough to also give you the definitions of a function. And in theory, you could also run help on help to get the documentation of the help function. If you execute code in the console, you can always retrieve it with the .last value expression. And this can be handy if you want to figure out what structure something is that you produced in the console. Next, I want to talk about the assign operator because it allows you to store a vector that you created in an object. So by assigning this combination of 8 numbers to the object named prime in the console, it doesn't execute the C function, but stores these 8 values in the prime object. So now in the environment, there's an object called prime that's 8 numbers long, and here are the values. You can also run help on the assignment operator by putting it into backwards quotes. And here you can see that you can also use the equal sign to assign values to an object, but I would limit the use of the equal sign to assign things within a data frame or a function and keep the less than minus operator to assign things to objects. Also, if you want to assign something to an object, but also execute or display what this object then looks like, you can put it into parentheses, and when you execute it, it will get assigned to the prime object, but also display the values. Next, I want to talk about brackets for indexing. So now that the prime object exists, you can access the values of this object with the square brackets. For example, give me the first value and you get 2, give me the fifth value and you get 11. A negative sign can be used to exclude that particular value. So now without the second one, you don't get the 3, but all the other prime numbers. And you can use the c, the combine function within square bracket, to give you the first 3 prime values. And if you use a minus before the c function, it will exclude the first 3 values, because what the minus does, it will get transferred to everything within the c function. So now you could exclude number 1, 2, and 3 from the prime vector. Now the square brackets can not only be used to index or extract values from a one-dimensional object like a vector, but it also allows you to extract data from a two-dimensional matrix or data frame, like the empty cars dataset has rows and columns with different characteristics about old cars. And you can also use the help function for that to learn where the data comes from and what the different columns mean. The str function reveals that you have 32 observations in rows for 11 columns or variables, and that all of them are numbers. And now indexing for a two-dimensional object like a data frame works like this. You still use the square brackets, but before the comma you define which rows you are interested in, and after the commas you specify the columns. So you could say, give me row 1, 15, and 19 and the first 4 columns. And the Mazda comes from row 1 and has these values for mileage, cylinder, displacement, and horsepower, and then number 15 comes here, and number 19 is the Honda Civic. If you don't write anything for the rows, you get all the rows with the 4 columns, same with the columns. If you leave empty space after the comma, you get 3 rows, but all the columns. And the minus sign works as well with -1 for row and column. You now don't have the first row, the Mazda RX-4, and the first column is also missing, so no information on mileage. You can also index a data frame by spelling out the names of the row or combined names for the columns specifically. So now you get only this one car from the first row and the first 2 columns in the order that you specify. So originally you have mileage first and then cylinders, but if you type cylinder and mpg for mileage, this is the subset of the data frame that you get. You can also use the dollar operator to extract values, like it shows here in the help documentation. And as you could see with the str function on empty cars, each column is indicated with this dollar sign. So you can extract the mileage from the empty cars data frame by using $mpg, and then you get all the mileages as a long vector of 32 values. Let us just check the first word 21, 21, 22.8, and these are the first 3 values. If you use one square bracket, it will indicate that you're interested in the first column of your data frame, and in the background, data frames are similar to lists, which you access with double square brackets, and then you tell it extract the first column from the data frame, and here you erase the structure. You just get one vector again, similar to the dollar sign. With only one square bracket, it reads it like an extraction while keeping the data frame structure. Now I want to move to the colon operator. It generates a sequence from 2, whatever you put before or after the colon. So you can generate the first 10 numbers, but it also becomes really handy for indexing. Instead of writing C 1, 2, 3, 4, 5 to extract the first 5 numbers from the prime object, you can use 1:5, which is identical to 1, 2, 3, 4, 5, and use that for indexing or extracting the values in a much neater way. The same works for extracting values from data frames, first 3 rows, first 4 columns. You have to be careful with the minus sign though, because you have to put it into the combine operator again to extract the first 3 cars. Otherwise, -1 to 3 would just create a longer sequence. But within the C function, added a minus, this means excluding those first 3 rows. You can also have your sequence go in reverse from 10 to 1, or you can use the rev reverse function on 1 to 10. Same for our prime numbers. If we want to look at them in the reverse order, just use the reverse function. Next, I want to talk about relational operators that you can use for comparisons. So one thing I haven't told you yet is that there are values in R called true and false that you can use for indexing or extracting values from a vector or data frame. If I combine true 4 times with false and true and false and true, it means that I want to get the first 4 values from the prime object, not the 5th and not the 7th. So 11 and 17 is missing. You can abbreviate true and false with T and F, so this will give you the same result. And if you do comparisons, they will result in a true and false vector of the same length. So if you ask which of the prime values is bigger than 10, you will get 4 falses followed by 4 true, because the last 4 values are bigger than 10. And you could use this for extracting values within the square brackets. So now it will neglect the first 4 values because they are false and only give you the last 4 because they are true. This is really handy because, for example, for a data frame like empty cars, you can ask which car's cylinder value is equal to 4. And now you can use this indexing vector, for example, on the row names of empty cars by adding it to square brackets afterwards. So now it will only show the cars where the cylinder value is equal to 4, generating a true. This would be a way to extract information from the data frame. You can also use these comparisons for subsetting the data frame, only showing the cars with 4 cylinders. The equal can be modified to !equal, which stands for not equal to 4. So now you will get all the cars that have 6 cylinders or 8. You can also display the cars that have a bigger or equal to 20 mileage, including the Mercedes 240D. And similarly, you can also subset your data frame to cars with a mileage below 20. There's one interesting operator for comparisons called %in%, where you ask whether the cylinder value is part of this combination of values. So either 4 or 8 will lead to a true, which is a quick way to neglect cars with a cylinder value of 6. Without the %in operator, you would have to combine 2 comparisons, which you can do with the AND or OR operators in R. So you could look at the rows where cylinder equals 4 or where cylinder equals 8, and it would give you the exact same data frame. You can use this to extract values for a more narrow window of mileage. So all the cars that have mileage above 20 but below 25. So this is a small subset here. You should brush up on your logical combinations of values. So if you have 2 values of trues and false, there are different ways to combine them, which lead to different results. So if both of them are true, of course you get true. But if true and false is combined, then it will lead to false. False and false is also false, and true and NA cannot be clearly identified logically, so it will give NA as well, because it doesn't know what the second term is, so it cannot say whether this is false or true. The OR is a bit different. It works as an exclusive OR as well, so if either of the cases is true, it will lead to a true. If both of them are false, then of course you get a false. But since one value is enough to make it true with the OR, true and NA will lead to true. So just be aware of that when you create different conditions that generate different vectors of trues and falses, how you will combine them. So if it's an AND, it will be displayed. So the first car has a mileage above 20 and below 25. But if either of those is false, it will get excluded. Because if you have 2 vectors and you want any position to be included, both statements have to be true when you combine them with an AND. So this was the example before. If your cylinder is 4 or 8, give me the results, including only the 6s. And one interesting point as well, with the exclamation mark, you can turn trues into false and false into true. Which means, as before, when we use this for mileage between 20 and 25, if you surround these results with an exclamation mark, you get the exact opposite. And now you would show only the cars that have a smaller than 20 mileage or above 25, but no values in between. There are 3 functions that you might find useful, but I personally rarely use them, called attach, detach, and with. So you might find it a bit cumbersome to always specify a column from a dataset with the $sign. So here you ask for cars that have 8 cylinders and a displacement above 350, and then you use this indexing vector to extract the mileage of those cars. And you see they're really small because these are big cars with big engines. But if you attach the empty cars data frame to the R environment, you will get the same result now without having to specify the object itself. So now you can simply say, give me the mileage for the cars from this data frame with cylinders 8 and displacement 350. And with detach, you can reverse this connection of the data frame to the environment. And now if you would try to access the mileage column, it says this object is not found. So I personally don't like to have these columns in my R scripts where other people wouldn't know from which data frame they come from. The same works with the with function, which needs a data frame and an expression, and then it will give you the same results. So with this empty car data set, give me the mileage of these cars. 2 interesting functions that might come in handy when you deal with indexing vectors. So vectors that are true or false are the any function that will simply tell you if any of the values in your vector is true true, and the all function that only comes out true if all values are true. And if you suspect NAs, there's one function argument within all that says na.rm, where you can say that NAs should be removed, and now this comes back true if all values within your vector are true. Another interesting function is the sort function that allows you to sort values from smallest to biggest. So these are all the mileages in the data set. And there's one function argument within sort called decreasing. And if you set this to true, they will go from highest to lowest. So by decreasing values. And one tip you can use, if you use the tab key on your keyboard, it will show you different function arguments. And you can abbreviate those if they are still uniquely identifying the function argument. Now the which function can be really helpful to extracting specific items of a vector. So for example, the maximum mileage you can see with the max function. It's 33.9, which we saw by sorting all the values. But now the question is, which car has the biggest mileage? So what you can do is use the expression with this equal sign. So compare all mileages from empty cars to the maximum of mileage. And this will result in a long vector of mostly false, and it's only true to this one car. And in theory, you could use this vector within square brackets on the row names of empty cars to extract this one value where this expression is true, which gives you the Toyota Corolla number 20. But what the which function does, it tells you at which position this expression is true. So it gives you number 20, and you can extract the value with this knowledge now. You can also ask which positions of the empty cars equals 4, and then use that for extracting certain values, or again the car names for which this condition is true. Moving on to the length function, it tells you how long a vector is. So remember prime, which contained the first 8 prime numbers, it has a length of 8. If you use it on a data frame with 2 dimensions, it will give you the length of the columns. So there were 11 variables, and that's what the length will give you for data frames. Moving on to the rep function for repeat. Here the help function can be really helpful because there are function arguments like times, length out, and each that you might confuse from time to time. And what the repeat function does, you give it a certain vector, and then with times you will repeat this vector 4 times. 1, 2, 3, and 4, repeating the combination of 1, 2, and 3 4 times. You can give times argument also a vector, which then specifies how often each value of x will be repeated. So the first item will be repeated 5 times, the second one 3 times, and the last one only once. Instead of times, you could use each. And now it looks different from the first one because times repeats the whole vector 4 times, and each repeats each element of the x vector as many times as you specify. So now you get the 1 4 times before it moves on to the second item. There's a function argument called length out, and if you set that to 10, it will repeat this vector as many times as it reaches the number 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, and it stops. And sometimes you have to create vectors with a very specific order of numbers, and then you can use the C function to combine them. So repeating 1 to 3 twice, but then 4 to 6 4 times. With C, you can create this vector, which is sometimes easier to wrap your head around instead of using these different combinations of x and times. So repeating 1 to 6, different number of times. You could also create this by 2 rep functions, where this times vector is generated with a second rep vector, where you repeat the 2 3 times and the 4 3 times, and then you get the same result. Now I want to talk about the sample function. There's an object in R called letters that gives you all the capital letters of the alphabet, and you could extract the first 8, and there are also the small letters. And what sample does is drawing values from a vector. You have to specify the size, so with letters for x as the vector and size 5, you would draw 5 random letters. If you try to draw 30 letters, you get an error because there are only 26 letters in the alphabet and you try to draw 30. And to overcome this, you have to set replace to true. By default, it's false. And now it will draw a letter like E and then replace it so it can be drawn again. And the table function on the last value, which is the export of these 30 letters, reveals E was drawn 3 times, O also 3 times, etc. Which brings us directly to the table function. Now I want to create a vector of cars that are sampled from this combined character vector, Tesla, BMW and Ford. I allow replacement and I want to draw 20 cars. And also in sample you can specify the probability, and when you use the help function you see that by default there's no probability set, but you can provide it as a vector of probability weights for obtaining the elements of the vector being sampled. So now roughly 0.5 of the draws will draw Tesla, and the other half is distributed amongst BMW and Ford with a slightly higher probability for BMW. And it came out exactly like that. Half of our 20 cars are now Tesla. I also want to create a colors vector where I draw from black, white and red. And what you can do now with the table, as shown before, you can ask how many cars are in the cars vector and how do the colors look. Here there's no probability assigned, so it was completely random and they should be roughly 1/3, 1/3, 1/3, but red is a bit overrepresented and black underrepresented. But what you can also do with table is combine two vectors and look for the intersection. So imagine you're at a junction and you write down the cars you see. The first is a black Tesla, the second is a red Tesla, etc. This table on two vectors gives you the combination. So Tesla and black is counted here, Tesla and reds are counted here, and there was no Ford in black, and 3 of the BMWs were red. You can use the T function in front of table to transpose the results table, and now you have cars on top and colors as rows, which you would also get by flipping the vectors. So the vector you put in first will be the rows and the second vector will count for columns. So now imagine for some of the cars you only noticed the color but not the type. Therefore I create a vector named cars with an A that gets assigned the exact same values as cars. But now I can use indexing. For position 5, 10 and 15 of cars, I will introduce an NA. So now the 5th car, the 10s and the 15s, we don't know the type. If you run table on a vector that includes NAs, those will be missing. So now the sum of this table that we still have in last value should only be 17 because 3 values are NA. And to make those appear again, you would have to specify a function argument within table called exclude equals null, and then it will create an extra row of cars where I didn't know the type. So now we have 1 black, 1 red and 1 white car that have an NA for the brand, and now the sum of the last value is 20, including all the values of the vectors. One cool function that you can use on tables is the addmargins function, and what it does, it will provide the row sums and the column sums of your table. So it will sum up all the BMWs regardless of color, which we knew there were 6, and also it will count all the colors irrespective of car brand, and we knew that there was 9 red cars. Another important function is the seg function. It starts at the first number and then increases by 1 till the last number, so it operates on a from to basis, and you can provide a by that gives the individual steps. So now you would count from 1 to 100 in steps of 7. You can also start at 100 and then count by steps of -3, and with length out you just keep counting until you have 20 numbers produced. There's also a function argument called along with, so now it would start counting at 1 and then as many steps as empty cars has columns. And if you wanted to count along the rows of a data frame that you have, you would have to specify this here. So give it the row names vector and then it would count from 1 till 32. So you remember that we had the mileage sorted from the empty cars data set, and what the cut function can do on a vector with numerical values, it creates 4 levels, and then instead of reporting the individual mileage, it just tells you within which bracket this value falls. So 21 is between 16.3 and 22.1, so it gets grouped into the second bracket. And this 30.4 mileage gets grouped into the biggest bracket because it is in between 28 and 33.9. So the table will reveal a distribution of your data set, that you have 10 mileages that fall in the lower bracket, 13 in the second lowest, and then 5 cars in the second highest and 4 cars in the highest bracket. As you can see, by providing these 4 breaks, it will create equally sized brackets. So this covers a range of 5.9 mileage points. Similarly here, 5.9. This is 5.8 because there wasn't a mileage, that's 22.2, and another 5.9. Just a quick explanation, the round parentheses and and a square bracket symbolize certain mathematical values for intervals. It means that for the square bracket, the value is actually included. So if x is bigger or equal to a, it will be within the bracket, and around parentheses exclude these values. So if you have square comma round, your value will satisfy this range when it's similar to a but smaller than b. And if you look at the help function for cut, you can see the arguments that you need a vector, you can provide the breaks, you can decide on the labels, and then decide also whether the lowest value should be included and if the interval should include the right value or not. Instead of a number for breaks, you can give it actual values. So now it will try to group everything to fit into 10, 20 and 30. And then you notice that some values are above 30 and they couldn't be excluded in the second interval. To avoid this, you can include the maximum value of your distribution within the breaks vector by combining it to 10, 20 and 30. Now the missing values have their own bracket level. And as I said, you can also specify labels, and now your first interval will be labeled with low mileage, second one with mid, and the third one with high. If your break vector goes from minimum to maximum with gaps at 20 and 30, you notice two values are excluded because those have the minimum mileage, which is 10.4. And as we noticed, the round parentheses exclude these values. So if you want them to be included, you would have to specify the right argument as false. And now the minimum values are included, and these two NAs at position 15 and 16 appear again. But now the maximum value of 33.9 is excluded. Okay, what does the unique function do? When we sort the mileages, we can see that some values are duplicated, some cars have identical mileage, and the unique function on any vector will show you the unique values. And you can see that it's now shorter, it's only 25 items instead of 32, and there are no duplicates anymore. To identify duplicated values, you can use the duplicated function, and what it does, it shows you the first time a value is duplicated. So these are the mileages from empty cars, and when 21 appears the second time, you get a true because it's a duplicated value. The 9th item is also true because the 22.8 already appeared at the third position. And now you could use this trues and false vector, flip it around, so turn all the trues into falses, and use it to index the mileage. And it's the same way, similar to unique, to extract only the non-duplicated values. You might be familiar with the iris dataset that has measurements of the flowers of 3 different iris species. And what you can do with unique is to extract the unique species values, and you can store this information in a species vector. Similarly, you could use the names function on the table of iris, because the names of a table are also unique and you would get the same values. One difference though is if you use unique, it will keep the level information of the species. If you go via names of the table, it will show you that it's now a character value. But for the next function that I want to show you, this doesn't really matter, because now I want to show you the for loop. So you start a for loop by saying that there's going to be some variable I or k or j that takes these 3 values, 1, 2 and 3, and you put all of this in parentheses after for, then you start a squirrely bracket where certain things will happen. So for now we will set I to 1, and given that we have a species vector, if we extract the first value, we will see it's setosa, and we can compare all iris species to this value, which will show us the first 50 being true and the rest false. And we use this for row indexing the iris dataset, keeping all the columns and storing this in temp iris. So now temp iris only has the setosa species, 50 entries and 5 columns. And within this loop, I want to plot the sepal width versus the sepal length. So the first 2 items using the plot function for x and y values. And with main, you can give it a title, which is handy to use the name of the species that you're currently looping through. Then you close the bracket, and now the for loop will go and set I to 1, 2 and 3, therefore selecting a different species each time, creating a different temp iris data frame, and create 3 different plots. So now you can check that I is 3, because that was the last value, and therefore species of I will give you Virginica, and that's the last plot that you see with the different values of sepal width and sepal length. But you can click back to the plots that were created during the loop, starting at setosa, second one versicolor, and then the last one. So this worked. If you want to automate loops a bit better and you're not sure how many species there are in a certain vector or data frame, instead of using 1 to 3, you can use length of species, which is 3. And now the temporary data set will contain the first 4 columns, but not the species column. And we use the boxplot function on it. And this will work on the complete data set. And what it does is looping through the species again, creating a boxplot for all the 4 columns that are presented here, giving you a boxplot of the different measurements for the different species. And yet another option for a for loop, instead of telling I to become a number that you then use for indexing a vector, you can let I become the species name itself. And here I use a parameter option called mfrow, where I now want to not show one plot at a time, but for 3 rows, different plots in one column. And now I don't compare iris species column to the first, second or third value of the species vector, but to the species name itself, which I will loop through based on the species vector. And now also I don't have to use species square brackets I for the title, but can plot the title directly based on I. The I value is now not a number, but the name of a species. And if we zoom in to this plot, we see that we have all 3 scatter plots in one chart. And at the end I set par mfrow to 1, 1 again, so that the whole plotting area will be used again to display the data. In this section, I will show you functions that allow you to analyze objects like data frames or tables. For example, dim will give you the dimensions of the mtcars dataset, which we know had 32 rows and 11 columns, but you can also very specifically ask for the number of rows or the number of columns. You can use row names to identify the names of these 32 rows. Col names will give you the names of the columns, and similarly, names will also give you the column names of this data frame. I will duplicate the mtcars data frame and store it in a backup object. And now we know that the first name is mpg for mileage. And if you want to change that, you can assign it a new name simply by putting it into quotes. So now mpg was changed to mileage. You can also change 2 names at a time by extracting the first 2 names of the data frame and assign it 2 new character values. And now you see that the mtcars backup data frame starts with mileage and cylinders. Other functions to investigate your data frames are head, tail, structure and summary. Head gives you all the columns of a data frame, but only the first 6 rows, so only the first 6 cars are shown here with their associated variable values. However, you could change that by providing an n within the head functions, where you can increase that to any number of rows that you want, now showing the first 10. The head function also works on one-dimensional objects like our prime vector, where you can show the first 5 entries, and tail is the opposite of head. It shows you the last 5 entries. Therefore, if you use tail on empty cars, you get the last 6 cars by default. Remember, with view, you can see the complete data frame in RStudio. str is a function that I use very often to get a glimpse at the data frame that I have to analyze. It starts with the first 2 dimensions as well, where observations are rows and variables are columns. And then it identifies whether the column holds numerical data or characters. And it also gives you the first items of each column. Summary is a very neat function because it gives you the min, the max, mean, median, and first and third quartile of any numerical vector. You can also use summary on an entire data frame to get the min, max, mean, median, and the quartile values for a numerical variable like the mileage. And one thing I want to point out, if you have a variable like AM that represents whether the gear is automatic shift or manual, this mean number, average, represents the percentage of ones in your data frame. So if you would use table on mtcars $am, it would show you 19 zeros and 13 ones. And if you would build the average of this, you get 0.406, which represents 40%, 13 divided by 32. You could also use this for comparisons. For example, if you ask which mtcars cylinder equals 4, you get trues and false. And a true in R is represented by a 1 and a false by a 0. So this now means you have 11 cars out of 32 that have 4 cylinders. And this number you would also get if you use the mean on this vector of trues and false. And since trues represent 1 and false represents 0, if you use sum, it tells you also that you have 11 cars with 4 cylinders. Okay, so the order function can be a bit hard to understand, but it's very useful to rearranging your data frames. So we had the mileage from the empty cars dataset, and order spits out certain numbers from 1 to 32. And in order to understand it, I want to give a quick, easier example. So imagine this vector of numbers, 132, 482. If you want to order these items, the order function tells you where each item is supposed to go. So the 8 is the 5th item in the vector, and it has to go to the last position. So the order value is last here. And the 6th item of this vector is here, and it would have to come on the 3rd position. The 1 can stay at the 1. The 3rd item of the vector has to come to position 2, and the 2nd item, which is the 3, would have to go here. If you want to extract the 5th value of your vector, it's the 8, and this has to go at the last position. So if we use this order vector in square brackets after the vector, it will rearrange it in perfect order. So going back to empty cars, it tells us that the item 15 has to come first, and the item 20 will have to be the last if ordered perfectly. So let's check that 17, 18, 90, 20, 33.9 is the biggest mileage. It has to go last, and the 15th value is here. With the 16th values, these were the smallest mileages, they would have to go first. And this is really helpful if you want to rearrange your data frame by a certain order. So now all these numbers that come out of the order function on mileage can be used for indexing in the square brackets on data frames. And now the cars are ordered by increasing mileage with all the associated variables. There is an option within order called decreasing. You can set it to true, and then it comes out in the reverse order, starting by the highest mileage and then decreasing. You could also use reverse on order to do the same, and then you can store this new data frame into a new object that you might call empty car sorted mpg. You can also order based on two variables. So for example, first order by all the cylinders, and then within the cylinders by mileage. So we use this order for rows, and for columns we just want to see mileage and cylinders to check whether this worked. And now you have it, first cylinders, and then within 4 cylinders increasing mileage, same for 6 cylinders and for 8. And if you want to change that, having decreasing mileages within the cylinders, you would have to use a minus sign in front of this variable. And now they decrease within the 4 cylinders from highest mileage to lowest. I already showed you the table function that allows you to count how many cars in your data set have 4, 6 or 8 cylinders. And if you add the sum in front of a table, it will add all these up to 32, which means that if you divide your original table by this sum, you would get the percentages. There's one useful tip for the table function where you can investigate whether your data set is complete. For example, in Gapminder, you have multiple different countries with data on several years. And if you do a table on country, you can check whether you have 12 years present for all of these countries. But instead of scrolling through and checking for the 12, you can do a table on table and see if all of the items of your original table contain the number 12. So all 142 countries, which you could check with names. See, now it gives you the names of the original table, 142, and each of those has 12 values. One thing you can do with a table is turning it into a data frame with the data frame function. So you would just wrap your table within the data frame function. And what it does, it turns the names of the table into a column with the name var1, and a second column is generated that holds the frequency of the variable. And now the structure of last value is a data frame with 3 observations. If you do a cross table on 2 variables, you remember that now it shows you which cars have an automatic and a manual shift within the 4, 6 and 8 cylinders. And in the help for empty cars, it shows you that 0 stands for automatic, which most of the cars with 8 cylinders are. But if you would try to turn this into a data frame, it would look like this. It creates 2 variables now, because that's how many went into the table. First variable is the cylinders, and for 4 cylinders you now have a second variable that's either 0 or 1 with the associated frequency. So this might not be exactly how you would want to represent the data, giving up the column and row structure that comes natural from these 2-dimensional tables, but there is a trick that you can do by using as.data.frame.matrix on the table. And now it keeps the structure of the table, but turning it into a data frame with again 3 observations, but now 2 variables. And data frames are a lot easier to work with than original table structures. Now I want to show you how you can use the is.na function. So imagine there's an example data frame with stores that tells you how many apples and oranges they sold, but you have 2 missing values for apples for store D and E. You can use the is.na function on the entire data frame, and it will return the same structure of your data frame, but now holding false or true values depending on whether there is character or a number or a missing value or NA. And what's really useful is the combination with the column mean function, because you remember true and false count as 0 and 1. Therefore, column means could immediately tell you whether there's missing values in store, oranges or apples. And now you know that's 40%, 2 out of 5 values missing for the apples column. And now there's one trick you can do. You can ask which position within the apples column is NA, so missing. The last 2 values would be true. So if you use them on this vector and index only the last 2 values, you could, for example, set those to 0, because maybe you know they don't sell them there, they actually can only be 0, and now the NAs are gone and 0 was assigned directly into this position. Just some extra information. NA stands for not available in R, so that's a missing value. Then you have not a number, and not a number will also be true if you ask it whether it's NA, but infinity or negative infinity are not NAs because they represent something mathematically, but the null object is neither missing nor there, so you don't even get a true or false on that. And there's a very specific not a number function where you can ask is NaN, and this will only return true for the NaN and not the NA. Now I want to show you how you use the apply function to work on data frames. So I created a data frame called sales where apples, oranges and peach is sold, and we can use the paste function to give the data frame some row names. Currently they are just 1, 2, 3 by pasting together the character store with the letters 1, 2, 3, so ABC, and separated by an underscore. And we assign this to row names of sales, which are currently just 1, 2, 3, but now sales looks like this. And now you can use the apply function to calculate fruit percentages. So the apply function needs 3 arguments. It needs a data frame, and all of these are capitalized. So a capital X will indicate that you're going to work on sales. It asks for the margin, either a 1 going row wise or 2 going column wise. And then a function is happening where X will be each value within a column, and you divide it by the sum of the column. So you would go ahead and divide 10 by 45, then 15 by 45. And this gives you these percentages. So you would know 60% of the peaches were sold in store A, because that's 30 divided by 50. And the orange percentages, 1/4 in A, half of them in B, and then 25% in store C. You could also go row wise and ask store A, what did you mostly sell? Most percentage will be peach. Store C, mostly sold apples. And therefore you just have to change margin to 1 to go through them row wise. But now one thing you have to notice is that it flips the columns and rows around. So now store, which was the row dimension, comes out as columns, but we already know the trick to use the transpose function on the last value. And now stores are here again. And now the row should add up to 100%, telling you that store C almost entirely sold apples, which we can check by looking at sales. And yes, 20 out of 25 items were apples, and 2/3 of store A were peaches sold, 30 out of 45. A bit more on generating data objects. You already saw here how I created a data frame for sales. You just give it the column name and then add some values. For a data frame, all of these vectors have to have the same length, but they can be of different type. So you can have a column with characters and other columns with numbers. But there's also an object called matrix that asks for data and then number of rows, number of columns, and how it's supposed to be filled, row-wise or column-wise. So if you hand over the sequence 1 to 20 and specify that you want to have 4 columns, it's going to fill this matrix by row equal true, row-wise from 1 to 20. So therefore, if we set this to false, it will go column-wise, 1, 2, 3, 4, 5 first. And if we want to have 5 columns, the matrix gets a little bit wider. For the data frame, I told you that it has to contain vectors of identical length. This is different for a list. A list can have combination of all kinds of objects. You could even store a list within a list or a matrix or table. So here I give it integers 1 to 10. Then for height, I simulate 20 normal distribution heights with a mean of 178 and 6 centimeter standard deviation. And then I store 6 letters. So list A now tells you that they're integers, heights, and 6 characters. So all kinds of different items. And the $sign indicates that you can extract them. So you can get the letters from list A. You can also use the double square brackets and type into it what you want, or specify the number for the position of what you want to extract. The match function is very useful to extract data from one data frame and match it to information of another data frame. So the New York City Flights 13 package contains multiple different data frames with varying information. And the flights data frame holds information on the time when a flight departed, arrived, the delay. It also has information on the carrier, but only abbreviated and not with the entire name of the airline. It has the flight number, the tail number, the airport of origin, and the destination. And now what I want to do is extract the name of the airline from the airlines data frame and match it to the flights data frame. So since the flights data frame is really big with over 300,000 rows, we generate a sub data frame that we call flights 100 that just holds the first 100, and it limits the columns to flight, tail number, origin, destination, and carrier. So that's now a much smaller data frame, but it will suffice for this example. And now if you look at the airlines data frame, you see it has 16 carriers with the longer name. And what we can do now is matching the flights carrier to the airlines carrier. And for all of our 100 rows, we get numbers indicating at which position the carrier abbreviation is found in the airlines data frame. So the first flight has the airline UA, and it tells us in airlines, this is position 12 for the carrier column. So position 12 UA is found for United Airlines. And now you can see we can use this numbering to extract the long name of airlines. So now we can put this expression that we used to find the matching number from carrier to airlines carrier after the airline's name in square brackets to extract the 12th position now from this name vector. So now we have all the long names and we can add it to our flights 100 data frame. And now flights 100 not only has the abbreviation, but also the long name of the carrier. The same would work for the airports, where you have an abbreviation in the flights data frame and a long name. So now we can generate an origin name variable and a destination name by matching the flight's origin or flight's destination to the airport's FAA column that holds the abbreviation for the long name. And that's how you can turn one data frame with lots of abbreviations to a more informative data frame. Another way to add information to a data frame would be to merge it. So now flights 10 looks like this. And what you can do with the merge function is to merge this flights data frame with the airlines data frame based on something that they both have, which is the carrier. And it will compare the carrier in flights 10 with the carrier in airlines and merge matching items together. So this would be the result. Based on carrier, it takes over the name from airlines and adds it to the flight 10 data frame. Something that might be helpful for mergers, if you deal with names or characters, there are often different ways how things are written, and the toupper function would capitalize your text, preventing duplicates where something is written sometimes capitalized and sometimes not. Or you could use the function to lower, where you make them all small letters. Now I want to show you how you can use R for mathematical operations and statistical tests. You can use R to add, subtract, multiply, and divide, and also for exponentiation. So you can use this sign to calculate 4 to the power of 2, which is 4 times 4. You can also calculate the square root of numbers. And if you want to calculate the cubic root of a number, you can use the power symbol, and your exponent now would be 1/3, and you have to put that in parentheses. And this is the opposite of 4 to the power of 3, so therefore the cubic root. Similarly, instead of square root, you could have written 81 to the power of 1/2 to get 9. One thing that's very powerful in R is vectorized operations. So the sequence 1 to 10, you can do multiplication on each individual item of the sequence simply by writing 1 to 10 multiplied by 2. You can also do addition on two vectors, which would mean that to the first item you add 1, to the second item you add 3, and then to the third item adding 1 again, to the fourth item 3, and so on. This is called recycling, where the shorter vector gets recycled for the operation as many times as needed to complete the longer vector. If you try to add a vector of the length 3 to a vector of the length 10, you will get a warning telling you that the longer object is not a multiple of the shorter one, because it will recycle, adding 1, 2, and 3, and then adding 1, 2, and 3 again. And then when it reaches the last number, 10, it can only add the first number of the vector and not the last two. It will still do it, but it comes with a warning message that your vectors don't match completely. And you might remember from the apply function where we calculated sales, I was using the following expression, function of x, symbolized by x divided by sum of x. And what this does, it knows that the sum of x is 35, and given that it can do vectorized math, it will divide this sum of x to each individual item of the vector x. Therefore, that's an easy way to produce percentages of a numerical vector, because 20 divided by 35 is 57%. So this vectorization can be really useful if you want to calculate the square of the first 20 numbers, and also if you want to get through all of the different exponents, like 2 to the power of 8, which is 2 times 2 times 2 and so on. You could put a sequence in the exponent and it will calculate all these different exponentiations for you with this short command. So that's 2 to the power of 4, that's 2 to the power of 10, and that's 2 to the power of 32. R can also do the reverse of exponentiation. So for example, log 2 of 64 will result in 6, because you have to multiply 2 by itself 6 times to get to 64. There's also a log 10 function, which tells you that you have to multiply 10 by itself 3 times to get to 1000. And there's also the natural log, that when you apply to 2.782, you get 1, because the exponentiation function for 1 leads to 2.78, so that's the Euler number. There are two more operations that you might not be too familiar with. One is called modulo and the other is integer division. So it's the double percentage sign. Modulo tells you if you keep dividing 13 by 5, you will come to the point where there will be a rest of 3. Similarly, by 9, there will be 4 remaining. And the integer division, which has a / in between the percentage signs, tell you how often you can fit the 5 into 13 before it's not divisible completely anymore. So this is 2, and the 9 only fits into the 13 once. And modulo can be helpful to figure out whether a number is odd or even. So if the sequence 1 to 10 is divided by 2, you can ask with modulo what is the rest. And for these odd numbers, dividing it by 2 will lead to a rest of 1. The even numbers can be divided by 2 until there's no rest anymore. Therefore, you could ask if there's no rest remaining. We know that these are the even numbers and these are the odd numbers. And you could make use of the if-else function, where you declare a vector of integers. And then within the if-else function, you say that when the integers modulo 2 equals 0, so there's no rest, then I will call those even, otherwise odd. And then you get this result. Of course, the trigonometric functions are also available in R. For this, you should know that pi is already stored as a number. And now you could ask what the sin and the cos of pi is. Notice here that this is representing 0. So e to the power of minus 16, that's a lot of zeros after the decimal point. And the cos of pi is minus 1. If you want to do calculation on degrees instead of numbers, you have to be careful, because R is working with radians and not degrees. You can always divide pi by the semicircle 180 degrees to get to this radians numbers, which now means if you want to get the cos of 90 degrees, you first have to divide pi by 180 and then multiply by 90. So the sin of 90 degree is 1 and the cos is 0, again represented by this e minus 17. If you would round the last value, you would get that. And if you want to change it to 45 degrees, then you get these values, where sin and cos are the same. You can also do vectorized operations again, where you provide the angle and use the degree to radians transformation to get your sin for multiple angles at the same time. Now, one fun thing we can do for plotting, we can create a sequence from minus pi to plus pi in steps of 0.1 and then calculate a y value for sin, which you probably call sine instead of sin, cosine and sine. And then plotting is very easy because it just needs the x and the y values. And we now have the y values for sin and cos. So plotting it would look like this, the beloved sinus curve. And with points, we can add points to the already existing plot. Now we're using the cosine values for y and the color red. And then instead of using dots, we can use the type O, which represents a line connecting the dots. Now I want to talk about cumulative sums, products, and extremes. So if you use cumsum on a sequence 1 to 10, it will keep adding the numbers that it has already seen. So 1 plus 2 equals 3, plus 3 equals 6, plus 4 equals 10, always adding the next number of the sequence cumulatively to the already existing sum. There's also a function called cummax, which will continue to report the maximum value it has seen. So with increasing numbers 10, 20, 30, it will report those, but then all the other numbers that are smaller than the already seen maximum will not be reported. It will keep telling you what the highest number was so far, and only if there's another maximum value it will report this. Similarly, cummin works in the same way. So imagine you test some medication for blood pressure and you monitor the averages over a day to see if the value goes down. The cummin will keep reporting the minimum value you've seen so far, and only if there's another minimum it will switch to that value. There's not only cumsum but also cumproduct, where you would multiply the first 6 numbers and keep adding at it. It also works in the reverse, where you then multiply 6 by 5, by 4, by 3, by 2, by 1. And that's kind of similar to factorial, which exists as a function, which in math you would write as 6 exclamation marks, 6 factorial, which simply says what do you get if you multiply 6 by 5, by 4, by 3, by 2, by 1, with the difference that factorial only gives you one number, cumproduct would give you all the factorials in between. So this is factorial 6, this is factorial 5, 4, 3, and 2. So factorial 6 would be identical to extracting only the max of the cumproduct. There's also the regular sum function that will just add up all the numbers you give it, like the numbers of the first 8 prime numbers. And there is a story about a German pupil in the late 18th century called Carl Friedrich Gauss, who described the normal distribution. So he was a quite gifted math student, and he found the lectures pretty boring in his school time. So the teacher told him to sum up all the numbers from 1 to 100, because he thought he would take a long time doing so. So with R, of course, this is no problem, because you could just sum all the numbers of this vector to get 5050. But what little Carl thought about for a while was that adding up all the numbers from 1 to 100 is equal to adding 1 to 100 and 2 to 99 and 3 to 89, because these all come back as 101. So if you keep doing that, you get to the point where you add 50 to 51, which means you would simply have to multiply 50 by 101 to get to the exact same sum. So he was able to solve this problem really quickly. You remember that with the table function, you could count how many items you have in 2 vectors, and with addmargins, you were able to add rowSums and columnsums. You could also use the colSums and rowSums function to work on a data frame like empty cars, where it would just add up all the numbers it has for horsepower or mileage, and it can also do this row-wise, so for all the cars in the dataset, adding just all the numbers it has across all the columns. Just be aware of that your complete data frame has to be of numerical type, because it cannot add up characters. There are similar functions called column means and row means, which gives you, for the columns, the average mileage, cylinders, displacement, horsepowers, etc. For row means it's a little less meaningful, because it will add up all these different variables and then just divide by 11. Now I want to talk about the aggregate function that is included in the stats package. That's of course natively available in R, and it allows you to compute summary statistics of a data subset. So if you want to calculate the mileage average for different cylinders of the empty cars dataset, you could simply use the aggregate function and then use tilde for this formula, like calculate y based on some x variable, and it will go through all the different cylinder types 4, 6, and 8 to calculate the average. So you have to provided a function and a data set. You can be quite creative with that by creating your own function and then in squirrely brackets specify different ways of calculating your results and getting the min, mean, and max and n as number of observations in one go. So now not only would you have the average mileage for these different cylinders, but also always the minimum and maximum within each cylinder type, and then reported ends. So you know there are 14 cars with 8 cylinders, and the best car gets you 19 miles with 1 gallon and the worst only 10. One thing I want to mention is that this results table is not too easy to access because it's a data frame with 2 variables, and the results are included and stored as this results table with 3 rows and 4 columns, and it's a list with different character names. So it's a little bit nested within the result. In case you want to continue working with some of these summary statistics, you could, for example, store the result in a results object, and then extracting the MPG item, you would be able to target the 3rd column of that item to extract the maximum values. So it's kind of a table within one column of your results data frame. In the help function for aggregate, it tells you how you not only can calculate one result based on another one, something we did here, but also one on many categories. So we could have calculated the average mileage for different types of cylinders, or automatic versus manual shift, how you can do many against one and then also many against many. And you can always run these examples directly in the help function to see the results, or copy them over and run them in the console. So this is 1 against 1, this is 1 against 2 dimensions, so giving you the brakes numbers for wool A, but tension L, M and H, combination of wool and tension. Here you calculate the average ozone and temperature for different months, and here you add up number of cases, number of controls for 2 types of variables, and then you get this cross-reference of number of cases that fall into these combination of variables. Now I want to talk about the norm function, specifically the rnorm function that allows you to simulate normally distributed data. So if you run rnorm 1, you get 1 value. For rnorm 10, you get 10 values, and those all come from a normal distribution with the mean of 0 and a standard deviation of 1. So that's the default. All these numbers will center around 0 with a standard deviation of 1, which you can see if you plot it. So you get 50 points centered around 0. And this, for example, would allow you to simulate male heights for 100 individuals with an average height of 178 centimeters. And then I use the round function to shorten the output. So these would be our 100 male heights. And you can use the hist function to draw a histogram that needs x as a vector, and with 30 breaks we tell it to roughly split the distribution into 30 bars, and then you can see that it approximates a normal distribution. If we change n to 1000 and repeat this function, you can now see that it's a lot smoother already. Here are some rounding functions that you can use in R. So imagine that you have x as this number. Ceiling will always round up to 3, for example. Floor will always round down, because round x, you know, it's less than 2.5, so it should round to 2. There is a truncated function where, regardless of what you have after the decimal point, it will only give you the top integer, so it will truncate everything after your whole number. With round, you can include a digits function argument to say how many digits you want after the decimal point. So round digits 4 will give you 4 numbers now after the dot. And significant numbers is a bit different, because with 2 digits it just includes 2 significant numbers that you would need to describe this number here. So by now there should be no surprise that there are summary stats functions like min, median, mean and max. All of these have the na.remove option that you can set to true if you expect there to be NAs in your vector of numbers. But now I want to point out that there's also the quantile function that gives you the 25ths, quantile, 75ths, the median, and then the min and the max. But within quantile, you could actually specify the probability where you want to see the cuts. So you could change that and increase it to a bit more fine-grained quantiles by looking at the 20th percentile, 40th percentile, etc. The summary function is very similar to quantile, as it also gives you the min, median, mean, third and first quartile, and the max. So as I already said, if there are NAs in your vector, you cannot calculate the mean unless you set NA removal to true or to T, and then you would get the results. Let us now talk about statistical tests that you can do in R. You might remember that with the rnorm function you could simulate random values from a normal distribution. Here it will be 6 male heights that are on average 1.78 meters with a standard deviation of 6 centimeters. And with the t.test we can compare them to 5 female heights where the average is 162 with the same standard deviation, and ask whether those are statistically significantly different. So this would be a Welsh 2-sample t-test, and it gives you the mean of x, the first vector, and the mean of y, which is roughly the average of what we simulated with our rnorm functions. And it asks if the difference between these two vectors is significantly different from 0. And getting data that is so different from one another, if it would come from the same normal distribution, this probability is around 1%. Therefore, you would conclude that males and females are different when it comes to height. If we access the structure of this last value, we find that it's a list of 10 containing many of the results that we saw here. But this structure is useful in case you want to access the p-value or some other parameters after you run the t-test. It's also helpful to look up the help again, because here you will notice that by default it uses a two-sided alternative, but maybe your hypothesis is that one vector of numbers is less or greater than the other. It assumes that the values are not paired, so they come from different individuals and are independent from one another, and that the variance equal is set to false. In our case we could have set it to true, and you can also specify the confidence interval of the results, because here the difference is 16.38 with a 95% confidence interval of -5 to -27 centimeters, and since it doesn't cover 0, it concludes it to be statistically significant from one another. Next I want to show you how to use the chi-square-test, which is also called the Pearson's chi-square-test for count data. And here you have the hair eye color available at a dataset in R, which counts the distribution of 592 students for male and female sexes, and the hair being either black, brown, red or blonde, and eye color brown, blue, hazel or green. And you see the different count numbers. The structure tells you that the data is stored in 3 lists with different dimensions, and we could access, for example, the hair and eye color for males only by specifying this third list item to be male. And now what I want to do is using the chi-square-test to figure out whether eye color is independent of hair color. And if that is the case, then you would assume that the brown hair, which roughly half of the students had, will result in a similar split when it comes to eye color, which means you would expect half of the brown eyes to go along with brown hair, and similarly half of the blue eyes having brown hair, same for hazel and same for green. And for brown hair, that's surprisingly the case. So here that's dividing each number by 279, which is the sum of this table. And here we see 51% of hair being brown. And now you can check 19% versus 35, that's roughly half. 18% out of 36 is roughly half. 9 out of 17 and 5 out of 12. But that's only one hair color, because when you look into the blondes, blonde hair is 16% of the data. But then when you look at the distribution within the green eyes, you see that it's 8 out of 33, which is 42%. So almost a third higher blonde connected to green than expected. And similarly for hazel is 5 out of 47, 16%. No, here it's underrepresented. And for blue eyes, 30 out of 101, that's 29.7%, so highly overrepresented. And then for brown eye color, if you're blonde, that's 3 out of 98, that's the most striking difference from the average 16%. So now when we run the chi-square-test on eye color for males, we get a p-value that's below 0.05, suggesting that hair and eye color are not independent from one another. And here you get a warning that the p-value may be incorrect, and to avoid that you can simulate p-values by setting this argument to true, and then you get a similar p-value based on 2000 replicates. Next I want to talk about the lm function that you can use to fit linear models, so a linear regression can be done in R. And here I'm interested in whether there is a relationship between the weight of a car and the mileage, where we assume the heavier a car is, the fewer miles you will get with a gallon of gas, and the lighter a car is, the higher your mileage will be. And for that you can run the lm function, where you just specify specify the data set, and a formula in which you try to predict y, the mileage, based on x, the weight. And it tells you that starting at the intercept of 37, which would correspond to a car of 0 weight, you have to subtract 5.34 miles per gallon for every unit of weight that you add. So if you go from 2 to 3, on average you have to decrease from 26 to 21, 3 to 4, going down from 21 to 16. And what's useful is there's the abline function where you can use this linear model with the intercept and the slope directly into your plot. So now that's a slope with a y-intercept of 37 and a slope of -5. And we can visualize this a little bit better by using the xlim and the ylim function arguments, which stand for the limits of your x-axis. We set it from 0 to 6, and for the y-axis we go from 0 to 40. And now if we add the abline, we see that it intercepts at 37 and then goes down with the -5 slope. Now I recommend to not only run the linear model, but use the summary function on the linear model, because it gives you your function call, so the formula and the data set. It gives information on the residuals and on the coefficients. So both of those are significant. You get significant code with 3 stars. There's a highly significant intercept and slope. You get your estimation with a standard error and a t-value. And also quite important, you get the r² and the adjusted r², which stands for the variance explained by your input variable, which means that knowing the weight of the car, you can quite accurately predict the mileage. With this variable alone, you explain 75% of the variation. There's still some variation left. Some cars are far away from the line, either above or below, but roughly speaking, 3/4 of this variation is already explained by the weight. And now if you add more variables, for example the cylinders, you now already explain 83 or 82% of the variation. And that's because once you include the cylinder information, like for example here by coloring 4, 6 and 8 cylinders differently, the model will now not only be one line, but it will try to fit a blue line specifically for the 4-cylinder cars, and then another line for the 6-cylinder cars, and another one for the 8-cylinder cars, explaining more of the variance than by a single line. And since the cylinders are 4, 6 and 8, if you give this information to the color, you will get the color that's standard for 4, 6 and 8 as the values. I recommend turning it into a factor, because then the colors will be 1, 2 and 3, and you get black, red and green, which is a bit easier to distinguish from one another. Keep in mind that with str on the summary of the linear model, you get the whole structure of this summary, and this allows you to access again individual results. So you could extract the coefficients from the summary and also the r² value. In case you want to include it in some write-up of your statistical models, you can access this number specifically. Now I want to talk about a few string manipulations that you can do in R. For example, imagine you have an object called US that simply stores the United States character as a vector 3 times. Then the sub function would allow you to look for the pattern E and replace it with the character 3 in the vector that you give. And you would see that a E gets replaced with a 3, but only the first E. If you want to replace all the E's, you would have to use the gsub function, because then within each item of the vector, it would replace not only the first E, but all of the E's it encounters. This might be helpful when you load data that you expect to be a number, but for some reason the decimal point is a comma, or there is a dash between 4 and the 5 and you would like it to be 4.5. If you try to turn this character vector, which you can see it is character vector, if you would like to turn this into numbers, the as.numeric function would give you 3 and A's, because it doesn't know how to turn these characters into numbers yet. But if you use the sub function, you could replace a comma with a dot. And now this, with the dots, R would know how to turn into numbers with the as.numeric function. 2.5, 3.5, only for the 4 minus 5 character you get an NA, but you could replace that with a 4.5. So what you would do is, you would in the first step assign numbers with the replacement of the comma, and in the second step replace the 4 minus 5 with 4.5, and then you could say numbers is as.numeric numbers. And now you can do all the calculations that you want. The grep function allows you to look for patterns in a character vector. So if you want to look for a certain airport and your flight's origin name, and you don't know the exact name that you're looking for, you could, for example, grab the pattern John in the origin name, and it would give back the numbers where it encounters these, and then you could use those numbers for indexing to get the proper name of the airport. The nchar function allows you to count the characters in a character string. So in the gapminder data, you had many different countries, and if you want to count the characters in each and every one of them, you could use the nchar function. Problem here is that the countries are stored as levels, and it cannot determine the number of characters in these levels because in the background they are just coded as 1 to 142. But you can turn factors into characters with the as.character function, and now you get your results, and you could store them in a data frame. I use the head function to only get the first 6 items, but here I assign country as the character of these country levels that are unique, and I count their number of characters. And now you would know that Afghanistan has 11 letters and Angola only 6. strsplit can be a useful function if you want to split a string into its items. You would give it a character that you can split on the spaces, and it would turn it into a list that holds as many items as there are once it splits them on the space. So this would now be 8 characters. So you could in theory count how many words you have in a paragraph. And since this is a list that holds 8 character values, with the unlist function, you could turn it into an actual string of characters. So now the last value is just a vector with 8 items. Next, I want to talk about the paste function. Imagine if you want to combine some characters with other characters or numbers. Here are the first 5 letters, and if you paste them to the sequence of 1 to 5, you will get 5 new character items, and within paste you can specify the separator, so you can have the underscore, or you paste them together with no space in between. For that, you could in theory use the paste 0 function directly, because in this function there are no separating options. If instead of 5 individual results, you just want to have 1 long character value, you could use the collapse function argument with a certain character, and what it will do, it will create 1 long string where everything is combined to 1 item, and here the default separator again is the space. If you don't want that, then use paste 0. So depending on the collapse character you want to use, you could turn that into a comma separator with space and then collapse this to this string of text. Print is a function that outputs any kind of object or text or number, and you can use it, for example, in the for loop. So imagine you want to calculate your savings or assets based on a certain interest rate of 7%, and you start with $10,000, and then you additionally save $1,000 every year, and you do that for 10 years. You can create a for loop where I takes on 1 till 10 years, and it will print the assets that you currently have, but then after that printed, it will add whatever you saved this year and multiply it with the interest rate. So you create these 4 objects and then run the for loop, and you will notice after the first year you save another $1,000 and you get 7% interest on all of that. Next year another 1,000 saved and 7% on everything you have so far, which would triple your assets in 10 years. If you cannot save anything within the year, you would just multiply the asset with the interest rate without additional yearly savings, and with 7%, maybe you know the rule of 69 or 70, that 70 divided by the interest rate or growth percentage of any kind equals the time necessary to double your starting number. So in the 11th year, 10 years after your start, with 7%, you nearly doubled the amount you started with. At the end, I want to briefly discuss some functions that are related to managing your workspace. Starting with the ls function, it lists all the objects that are currently in your environment. You could also look at some of these in your environment tab and then click on them to see the data. Objects would do the same thing, but object size can be used to infer the size of the data. So the object with over 300,000 rows, that's 40 megabytes big. The smaller subset with only 10 flights is only 2,000 bytes. You could remove an object like flights 10, and now it's not there anymore. If you want to remove all the objects, then you can hand over a list that holds the name of ls. So this would not work on a single character, but a list of all of these objects. So it's often good to include this line of code at the beginning of your script to clear your entire workspace. You could save all the objects you have created during your analysis by creating a file, for example, workspace, and then call it our data. And with get working directory, you see what your current directory is. So now our data would have been stored in the documents folder. You can set the directory with the setwd function, where you give it a directory, but there is a shortcut where you can use this expression to set your working directory to the location where your R script is currently based. So if I run that and ask again what my current working directory is, it's here for my YouTube channel, the base R functions folder for videos. And if I save the image now with the DRI function, I can list the objects that I have. And here you can see the workspace R data file. And if I now remove all the objects from my current workspace, you see that my environment is completely empty. There's nothing there if I use ls, but I can load the workspace that I just saved and continue working by using the load function. And this is looking for a file, and here I can give the directory where the file is located, or just give it the name of the file, assuming that it is in my current working directory. And now I load it and list all the objects again, and there should be plenty now. You can use the history function, but also click on the history tab to look at all the functions that you've used during your session. And if you work in the console and try out a lot of code with history, you can then decide to highlight a few lines of code and copy them over to your source file into your script, or load them to the console again. If you want to install a new package, then you can use the install.package function and just hand over the name of the package. There's also a packages tab where you can click on the install button and then look for certain packages. So maybe you want to do some Bayesian statistics. There are already many packages here. One very common package for statistical test is the chisq package, and you can simply install it or use the install packages chisq code, and then with library chisq you would load it, but you can also look at all the packages you have and simply click on the checkbox to load it to your environment, and then you're able to use all the functions that are in the package and all the datasets that are included. Also related to your workspace is how many digits you want to see by default, and you can change that with the options function. And now by default you would see 6 digits of pi and all of the numbers that you calculate and simulate. So you could, as always, use the help function to learn more about options. One other thing you can change besides digits is the scipen option, which influences how many digits you see for scientific notations. So when you write 10 million, it would come back as 1 to the power of 7. Similarly, if you write 1/10,000, it would be notated scientifically as 1 to the power of -4, because you move the decimal point after the 1, 2, 3, 4 steps to the left. But now in options, you can change scipen to 3, for example, and then 10 million will get displayed as 10 million, and small numbers without scientific notation. One option to load data would be the read.csv file that needs a file name, including the directory, whether the data has a header or not, so column names, what the separator is, and how you want to deal with decimals, and also if strings should be considered character or factors, and by default strings will be turned into factors, and I prefer to set this to false. So here I'm loading the file US spending CSV. You have to be careful to use either double backward slash or a single forward slash, and you cannot mix them in between, because a single backward slash in R is an escape character that you can sometimes use to indicate tab stops or parentheses, and in my CSV file the separator is a semicolon, which you can see here in the preview. So each value is separated by a semicolon and the numbers hold a comma as a decimal separator, and in the CSV file you can specify that the numbers are indicated not by 3.2 but 3,2. And now you can look at the spending of the US in billion for certain main and subgroups. Here you have the structure, all the different items are characters and the numbers are proper numerical values. And now you can create a new column in spending called %, where you divide every spending by the sum of the spending and round to 2 numbers after the decimal point, and then use a separator for the paste function to add space %sign. And now there's another column that tells you that in the US spending, education is 1.79% of the budget, Medicare and health 25.2%, social security 32%. And now with write.table, you can use the spending object and store the results in an updated CSV version, you run the code, and then there is a new updated pending item available. So congratulations, you made it to the end. Thanks for watching the entire video. I hope you learned a lot of useful functions that are basic in R, but help you to produce many interesting results. Please consider subscribing to the channel for more videos related to R, and if you liked the videos, please leave a like. Until next time, here at the Data Digest. Bye bye.